Hello, everybody. Welcome to this webinar of the Navigate project. It is on industry transformative change towards carbon neutrality. We have 4 presentations, but before we go into the details of the presentations, just give me the opportunity to shortly introduce the Navigate project. We are in our 3rd year currently of the 4-year project, and it is about advancing integrated assessment models and support for climate policy making. It has different work packages on improving the integrated assessment models, and then do an overall synthesis and model intercomparison. And we have different systems then that can change. So more on the production side, the transformational structural change and technological change work package. And this webinar here is on the industry decarbonization, located in that part. We also have land use transformation, more macroeconomic transformations, also socio-technical energy transitions and investment strategies. Here we particularly focus on the industry sector, and we have quite a interesting and exciting collaboration with, I think, 17 partners all over Europe, including also groups from Brazil and China. And yeah, so it's very diverse regionally and also disciplinary. Housekeeping rules for today. So you will be deactivated by default, but you can raise your hand in the Q&A sessions and the final discussion with these buttons, or you simply write your question into the Q&A. We have 4 presentations, as mentioned before. This includes Q&A, and at the end, a 25 minutes general discussion. So we start our menu with Mariësse van Sluisveld with a more global perspective on industry decarbonizations, especially heavy industry. Then Alexandre from COPPE in Brazil, and he talks about biomaterials with the specifics on Brazil, but also in the end given an outlook to the global modeling. Silvia here from PIC, my colleague just next door, when the home office period ends. So she's going to talk about electrification of the EU energy sector. And in the end, we have Panagiotis from E3M in Athens on the economics also and the political economy of decarbonization in energy-intensive industries. Okay, so this rounds up our menu. You see there's a lot of content, and the contents come thick and fast. So I give now way to Mariësse. She holds a PhD from University of Utrecht, and she works since 10 years at the Environmental Assessment Agency, the PBL, as it's usually known. And in recent years, she covered mostly development and analysis of industrial decarbonization pathways for Europe. So Mariësse, please go ahead with your presentation. I will unshare. And now you can go ahead. Thank you.
Yes, thank you, Nico. Good afternoon, everyone. A big hello from PBL Netherlands Environment Assessment Agency. I hope you can see my slides by now, and then I'm ready to go. Also, big thank you to the Navigate team for having me here, and for the honor for setting the scene to this afternoon. And today I want to talk about the industry sector and what the sector needs to do to stay aligned with the Paris Agreement. And I took the liberty to adjust the title of my talk a little to reflect the one question I want to try to answer today. And that's basically net zero. how should that be adopted into the future of the industry sector? And I think there is an overall consensus about how economies across the world should converge towards a certain zero emission point by a certain time, and also with a clear direction for the power generation sector. But how does this work for the other sectors, like industry? So yeah, for the real world, the race to net zero has been translated into the literal adoption of the economy-wide target across the wide range of industries. Now about 700 companies have committed to net zero or carbon neutrality or zero carbon commitments, and at least those that have been registered into the zero carbon tracker. And this collection also includes net zero commitments by industrial sectors, whom are now branded as hard to abate sectors. So that's interesting, of which the majority has pinpointed this endpoint achievement to the 2050 timeline, although there are some that have a 2030 target. However, as also underscored by other researchers, the degrees of freedom in formulating a net zero target are rather large, leading to a majority of corporate commitments to bank more on carbon offsets than achieving actual reductions within the production system itself. And in the absence of further details, there are difficulties in judging whether these net zero commitments show ambitions of real climate leadership, or whether it's more greenwashing. And the science included in the IPCC also does not offer much of a different perspective on net zero either, as a wide range exists for changes in total direct emissions, leaving much of the mitigation potential to other parts of the global system. And based on this figure showing the carbon emission reductions on the y-axis and the final energy changes on the x-axis, you can basically deduct that sort of anything goes. Only a few integrated assessment models are able to present pathways in which the industry sector interprets the net zero target as something that is internalized within the sectoral boundaries of the industry itself. However, further details on how this can be done within industry is usually not presented, as is also concluded by earlier papers by other colleagues in the field. So, to contribute to this lack of understanding, we basically ask ourselves the question, what can a more technology detailed IAM, an integrated assessment model, say about what net zero means for industry? Luckily enough, PBL Netherlands Environmental Assessment Agency owns an integrated assessment model called IMAGE. And IMAGE is a model, an integrated assessment model that includes representations of the economy, the land system, and the climate system. And as it exists already for quite some time, PBL had enough time and opportunity to invest in improving the resolution of the model in many directions, including into adding more explicit representation of energy demand modeling, and also specifically the industry sector. However, the usual level that is being reported on stops here. But in the background, we actually have various explicit representations of industrial sectors running in the background. Running along in the computations in the background. And within IMAGE, industry is represented by a mix of top-down and bottom-up formulations. And overall, we cover all the industry sector classifications that are included in the IEA energy balances. And the choice for which method is applied is basically dependent on whether we as modelers have been able to come up with a generic formulation for a certain industry. So the more heterogeneous or data-rich a sector is, the more detailed the representation in IMAGE is. And although the degrees of detail in these explicit representations vary, they range from more explicit material systems, where explicit detail is added in every part of the value chain, or the life cycle of a material or product, to a reduced representation that focuses more on just the energy uses within that sector and the potential changes there, and therefore ignoring perhaps a broader production system innovation trajectory. What else to say there? Well, I would say overall the subsectoral representations portray a rather linear system still, with static formulations of demand that operate more or less in isolation of the rest of the represented system. And despite having explicit formulations of secondary routes and detailed end-use submodels. So more or less still a rather conservative representation of industry. And based on the model structure as we have it right now, one can already deduct what options image has on the menu for industrial decarbonization, which are the blue squares on this figure. And as shown here as well, the selection of options is more diverse on the energy innovation level and becomes less rich on other levels of innovations, such as the process innovations that I could classify and the material innovations. However, we can still cater to solution strategies that are not fixed options on the menu, as modeling gaps can be supplemented with imposed storylines, which is what we have applied in our study to find out what the potential of industrial decarbonization as discussed as of today could mean for basically the industry within a net zero context. And with all these modeling options and narrative-driven storylines, we could create a scenario matrix. And based on this scenario matrix, we could do analyses. So if we look at the scenarios where we squeeze out everything that the image model can deliver in terms of decarbonization, which is basically equal to what being in line with the Paris Agreement and the economy-wide net zero movement, we see that on a subsectoral level, most of the carbon industries will not be able to internalize the net zero commitment on a subsectoral level. So for most scenarios and regions represented within the image model show the presence of residual emissions until the end of the time horizon. And the only exception is seen for the pulp and paper sector, which can help to offset the industrial emissions elsewhere. But in general, it's not enough to meet a net zero deadline on 2050. But we find that the industry can reach net zero if we include the wider system changes within their scope of assessment. However, unlike the current interpretations of the net zero commitments, pinpointing this achievement on 2050, we see that in the results of the image, the majority of the scenarios might pinpoint this final endpoint achievement more closer to the 2040 timeline. Now, knowing that, we might wonder what is actually happening on a strategic level. And if we let the model freely decide a cost-optimal pathway, it shows that it has a high preference for adopting carbon capture and storage solutions for the carbon-intensive industry. So the steel sector and the cement sector are very dominant here. And this will cut emissions the most for these sectors. However, with further incentives, more focused on technology pathways, we see a shift in mitigation potential to other strategic options. And we see that the preference shifts from carbon capture and storage to, amongst others, electrification, there's this one, and fuel switching. And what I did not mention just now, it's like, let me go back one more. If we focus on CCS, then there is still, on carbon-intensive industries, then there is not enough attention or incentivization for other industries to join in on benefits from tailoring the decarbonization policies to these sectors. And the other industries may create a bottleneck to mitigating the industry sector any further. Whereas if you adopt other more options that are more targeted towards electrification and fuel substitution, then the other sector may benefit as well from this, showing that there is a lower degree of residual emissions left on the balance. And the net negative emissions that are created by, amongst other, the cement sector and the paper industry can balance out the remaining residual emissions from the other sectors. therefore creating net zero.
2 minutes.
Yes, I'm close to finalization, so that's good. And to lump sum all the demand management and circular economy scenarios results, what we see then, if a stronger set of demand manager or circular solutions are incentivized, it shows that it reduces the total mitigation challenges for industries substantially. So you could see the little jump there. However, new risks arise for those sectors that do not have a clear alternative to primary production. So that could be something that could pose a risk after 2050. So that's a trade-off. So now, in my final minutes to wrap up and to recap, what I've learned from this study is that corporate net zero commitments that bank on offsets to the other demand sectors or the other parts in the economy or in the climate system. These are also phenomena that are represented in the image model. So if we allow this to happen, then we should learn from this model study that it's not the 2050 endpoint that we should strive towards, but it's more closer to the 2040 timeline. And if we do not like the results as they are right now, then we have to conclude that the current representations in the image model, mostly reflecting a continuation of today's industries, cannot longer continue like that. Without any further changes in those kind of structures, the model does not think there is any additional emission or decarbonization gains to be achieved. And this requires that we should think also about incentivizing and including more breakthrough innovations into the model structure. And interesting enough, I guess, also in policy for more or less, I think the industry sector is in the real world also more a reflection of the status quo. And also a wider spectrum of solution strategies should be included into models and therefore also in, I guess, in policy design. And although I have much more to tell and to say about this subject, I want to keep it to this. And I want to thank you for your attention.
Yeah, thank you very much, Mariësse. I give applause to your presentation on behalf of 4 in the audience. So we have a little time for Q&A. And there is a question by Kimon. He asks, do the demand side measures or other demand side measures consist? No, do the demand side measures consist in material substitution? Are any of the trade-offs expected there? From substitution with timber and indirect land use change emissions, for example.
Yeah, so demand management options are not dynamically included into the image model. They're all based on static representations of statistical models. So it's like trade-offs are, if they are there, they are imposed by us through the storyline that we implement into the model. So for the moment, there are no included trade-offs in the sense that if we implemented it, then it is deliberate. But on the second half of the question, I've only focused more on the industry system, and there might be obviously effects in the land system as well, but I didn't look at them. So this is definitely interesting and deserves some further attention.
Okay, thank you very much. So I do not see another question. So we come to our next presentation by Alex. He is from Brazil, from the university in Rio de Janeiro. He joins COPPE with Roberto Schäfer and in a leading position. And he is important in the development and application of various integrated assessment models like the COPPE model, but also sectoral models like for power systems and oil refineries. And this is also part of his where he's currently mostly involved, namely to develop a more material materials module and petroleum refineries, including biorefineries, and include this into the COPPE model. He has published more than 150 articles, so very impressive, and guided 46 doctoral theses and 90 master theses. So that's quite an achievement. And now we are excited to hear about biomaterials in Brazil and with an outlook to the global modeling also. Alex, the floor is yours.
So thank you. We're going to share my presentation. Can you see it?
Yes, but
it's
going
working.
to press
okay.
presentation.
Okay. Now it's fine?
Yes. Now.
Okay,
now
thank you. So let me start. So thank you for this invitation, and I'm going to present mostly the results of this paper. Actually, we have different papers related to the production of biomaterials, and now also some papers and some studies related to the production of electric materials or hydrogen-based materials with CO2 from DEX. But I'm going to focus here on the case of biomaterials and through the lens of a national integrated assessment model, the Brazilian integrated assessment models. But as Nico said before, I also can discuss a little bit about what we are doing now with our global COPPE model, our global integrated assessment model. So we have different questions when we started this type of studies. We have different studies, as you can see, but I'm going to focus on this paper. And to this paper, we have different questions. But I think a major question here is the role of biomass in climate mitigation scenarios and the role of petroleum refinery utilization. So how the petrochemical industry will be in the next years or in the long term, given the fact that most of the feedstocks in the chemical industry comes from petroleum refineries. And as some refiners in the world, as the refining industry in the world knows, now they are thinking about diverting naphtha that would be used for gasoline to feedstock production. But actually, rephrasing this strategy means that without replacing naphtha, propylene production and other petrochemical feedstocks that came from petroleum refineries, some petroleum refiners will keep their production, will divert more naphtha from the gasoline pool to petrochemicals, but also will keep their run and will co-produce fuels at very low shadow prices. What I mean here is it's impossible to reduce to zero the utilization factor of petroleum refineries without addressing petrochemicals. And petrochemicals demand will increase because of the energy transition. We know that. And without addressing this supply, some fuels will be co-produced with naphtha, with propylene, because the production of these fuels is part of the production of some oil refineries. So we want to address this in our national model and also in our global model, but I'm going to present results from our national model, which is the Blues National Bottom-up Model. Is a model focused on the Brazilian land use and energy, and now the petrochemical and material sector in Brazil. And we are doing some implementation and some tests as of today to have the materials model and the petrochemical industry in the 18 regions of the COPPE model, which is a global bottom-up integrated assessment model. But I'm going to present the results to Brazil and to see how these results can show some interesting findings to us to be discussed by us. So I'm going to present fastly this. This is more for the chemical engineer. This is my origin in the university. So just to show you that we have to add some technologies to the Blues model and also to the COPPE model, to the integrated assessment model, in order to present this co-production, this available co-production of petrochemicals or feedstocks for the chemical industry related to the fossil fuel industry, but also to the biomass industry and also to the hydrogen industry. So we have different routes, different technologies that can produce petrochemicals. And the most important petrochemicals are the ethylene, the propylene, and the BTX, as you can see here. So these technological pathways, these technological options were added into BLUES, and now they are added also into our global integrated assessment model. And also we have in our models also some options for disposal, because of we have to understand the energy, the greenhouse gas emissions related to plastic disposal and to petrochemicals disposal as well. So we have 4 possibilities in our model, and obviously the long lifetime materials are an option to reduce, at least for a while, the emissions, the greenhouse gas emissions from the disposal options. So we have also this option as a way to deal, and these are very important to deal with greenhouse gas emissions, and these can be very important, particularly in the big budget scenarios. We don't have here in this presentation results for big budget scenarios, but we know that if we can delay some emissions, given the long lifetime materials, given the storage of carbon in petrochemicals, in plastic, these can have some implications for the big budget scenarios. We have run we run different scenarios and different sensitivity analysis in our paper. This is the paper. I have to point here. This is the paper I'm presenting now, and we have different scenarios and different sensitivity analysis. Actually, we have from the last Q&A section, we have some scenarios also related to materials substitution, but I'm going to focus here because of time. I know I have time, and I'm going to focus here on this 2 set of scenarios. My focus here is to show how having the biomaterials model on provides some interesting fights to us. So my focus here is we have this biomaterials model in the integrated assessment model, in our integrated assessment model, and I'm going to turn on and turn off this module in order to see the difference between the results. So firstly, we are going to present now the results and to discuss a little bit the results. We have here a baseline scenario without any carbon budget and a well below 2 degree scenarios. This is a full century scenario with a 600 budget to the emissions of CO2 in the full century scenario. So we have here the results to Brazil. And the 2050 scenario, the 2050 results show us that in the well below 2 degree scenario, with the biomaterials on, turning on the biomaterials in this case, we have a lot of production of biofuels, as you can see, and these biofuels are produced with deep changes in the land use in Brazil. So as you can see now, for this result to be feasible, we have here some land use change in Brazil. Mostly we are reducing the degraded pressure in Brazil and increasing the recovery pressure, and also having some integrated systems. So as we can see here, our model changed the way the land is used in Brazil in order to provide this increase of the biofuel production. And as you can see here, most of that is diesel from BTL plants, jet fuel from BTL plants, and ethanol, the ethanol plants in Brazil with CCS, so CCS for the production of ethanol. Now the case of the petrochemical, because of we are producing a lot of green diesel and a lot of jet fuel, a lot of clean jet fuel, we are also producing naphtha. Naphtha is a car output from these BTL plants. It's impossible to only produce diesel or only produce jet fuel in these plants. So we are co-producing naphtha. Without the biomaterials on, this naphtha will compose the pool of the gasoline pool. But with the biomaterials model on, what happens is that 21% of the naphtha in steam crackers in Brazil became bio-based. So most of this naphtha will be used by the petrochemical industry in Brazil. And more important than that, a third of the total chemicals demand in Brazil is met by bio-based petrochemicals. So we have here different situations that we can see in our integrated assessment model. The electrification frees up ethanol use for ethylene production. This is a point. And also the BTL production of diesel and jet fuel co-produced naphtha that can be used by steam crackers in Brazil. This is a least cost optimization result with the carbon budget. Here we are detailing this result. I'm not going to detail these results here, but just to show that we can see results for ethylene, from propylene and PTX and so on. A major message here is what happens when we have the biomaterials model off, when we turn off the biomaterials model. As expected, there is less biomaterials. This is a truism. This is a trivial result. Without the biomaterials model on, there is no biomaterials. There is only a slightly production of ethylene from ethanol that is the existing plant now in Brazil. Brazil has a plant that converts ethanol in ethylene. So there is a green ethylene as of today in Brazil. But most important than that, green naphtha from BTL, there is no green naphtha from BTL. This green naphtha goes to the gasoline pool. There is no naphtha as feedstocks to petrochemicals because there is no possibility for that. So we are going to produce biogasoline, green gasoline. And this can delay also the electrification of light duty vehicles in Brazil. We are producing diesel from BTL. We co-produce naphtha, a very cheap shadow price, a very low shadow price naphtha from this plant. And this naphtha will compose the gasoline pool, giving more competitiveness to this type of product. But having the biomaterials on, we have another type of result.
Alex,
Hence,
Alex,
okay.
Please 1 minute.
Yeah, I'm finishing. Hence, a major message here is to produce naphtha, oil refineries mandatorily co-produce fuels. So in order to supply the petrochemical demand, we are going to produce fuels, and these fuels will be very competitive. So we have to address different pathways to supply the petrochemical feedstocks. And as we can see, by turning on the biomaterials model in the blues model, we have an interesting finding that shows that the petroleum refineries will decrease their utilization factor. We can decrease the utilization factor of petroleum refineries by turning on biomaterials in the blues model. The last slide is that one. We are doing a lot of things here. This is a type of picture that shows that we are cutting a head and another two heads. We find another two heads. This is the legend of Heracles. The meaning here is that we are not going to finish this job, but we are trying to address different issues as of today. So first one, we know that the BTL is a kind of silver bullet of our model. We have to understand better what are the real possibilities of this technology, because this is a major biorefineries that can produce fuels, electricity, and materials. So we have to understand that better. We are now implementing a material demand modeling in our two models. So in order to have a kind of material service demand and to see the substitution between materials, we are starting this type of study in our group. Also, trying to better represent some options for recycling and, for example, the balance of fertilizers and chemicals, and detail the case of ammonia as an energy carrier and fertilizer. And as I told you before, we are improving our global integrated assessment model, named COPPE, in order to have the petrochemicals, but also many technological pathways to show how the materials in the world in the world energy system can be seen as an opportunity and as a challenge to the energy transition and for the decarbonization of the energy system. So thank you. Sorry, I think I passed 1 or 2 minutes.
Yeah, thank you very much, Alex. I think some of the participants may have some detailed questions on the modeling that I asked them to post in the Q&A section. And we move over to Silvia. And Silvia, my colleague here at PIC, holds a PhD from University of Sheffield in material sciences and engineering. She worked at Cambridge Carbon Capture Limited as a chief scientist and now joined since 2018 for the Navigate project, the Global Energy Systems Group. And she focuses on the industry and energy transition in Europe and at the global level. So, Silvia, the floor is yours.
Yes, thank you, Nico. Good afternoon, everyone. Thank you for joining this webinar today. I'll share my, oh, wait, I shared the wrong screen, sorry. Share screen. Let me know if you see my slides in full presentation mode.
Not in full yet, but we come closer. Yes.
Right now? Perfect. Okay, yes. So thank you for joining today this webinar, and I'm going to present the results from a paper we published last year where we investigated the CO2 reduction potential for the European industry via direct electrification. So before I dive into the results of the paper, I want to give a bit of a background information of why we decided to conduct this analysis. So we wanted to answer this question, right? So we are on the edge of an electrification era. Is industry prepared? If we read any climate mitigation scenario, if we check any climate mitigation scenarios or read any roadmap, climate mitigation roadmap, we see that electrification is really at the core of these decarbonization strategies. And there are many reasons. One of these is certainly the environmental driver, right? So we know that electricity is easier and faster to decarbonize than on electric fuels. The plot on the left of this slide is taken from the IEA net zero roadmap that was released last year. And we see that where really the decarbonization of the power sector is the principle behind the possibility to reach the net zero target. And we see here, we have a picture of how the power sector would look like in a net zero world in 2050. So 90% of the electricity is produced by solar PV and wind. So the technological advancement of renewables is really pushing for electrification. Yeah, we have another driver, another important driver, which is the economic one. So renewables are not only advancing very fast from a technological point of view, but also they are becoming increasingly cost competitive with fossil fuels. And in some countries, they indeed are already cheaper. So the panel on the right is also taken from the IEA net zero roadmap, and we see the levelized cost of energy of different technologies to generate electricity in Europe in 2020. And we see that solar PV and wind are already the cheapest option. So in a world where we have increasing availability of clean electricity and where electricity might become cost competitive with fossil fuels, then we have to consider what are the implications for all the end-use sectors that interface with energy markets. So obviously also in this case, what is the future for industry? And we already seen that for the mobility sector, they are moving very fast towards electrification. The residential sector, heat pumps are becoming really the main solution to decarbonize the sector. And then we have industry. And when industry, when it comes to industry, there is not so much consensus on the role of electrification, and there is not so much information and clarity of what is the potential to electrify industry. So that's why from this, we move to our analysis, and we focus on the European industry, and we try to identify available electric technologies that can be applied in industry. We try to estimate the technical potential for electrification of industrial processes, and then estimate energy savings and decarbonization potential. So now I dive into the results of this study. So as I said, first of all, we identified a portfolio of available electrification technologies. This table summarizes these technologies and it classifies them based on operating temperature, technological maturity, potential applications, and efficiency. And what we found is that electrically powered technologies can cover the whole temperature spectrum that is relevant for industrial processes, even for very high temperatures. We found that electric technologies are mostly already mature and well established in industry. However, when it comes to their application, they are mostly used for small scale productions. So when it comes to scaling up these processes, industry prefers to use combustion systems. And the reason for this is in the difference between the cost of electricity and gas. On average in Europe today, electricity costs 3 times more than gas. So obviously when the production is large, industry prefers to consume gas rather than electricity to reduce the production costs. And then there is another component that is very important, and is that the substitution of combustion systems with electrically powered technology could lead to significant energy savings. And in our study, we found that a full electrification of industry could cut 20% of the energy consumption of today, of industry in Europe today. So once we gathered this information on technologies and energy uses in industry, we tried to envision how we could move from today's situations of status quo to leashing out the full potential of electrification in industry. And for this, we envisioned 3 stages. And this plot in the slide represents what we call an electrification map. And now I will guide you through how we kind of derive this graph. So we started by analyzing what is the current electrification level in industry, and we found that around 20% of the useful energy demand in industry, in the European industry, is currently electrified. As you can see from the yellow shaded area of the plot, this shows what is already electrified, and you can see that there are huge differences across the different industry subsectors. But what is clear is that there is huge potential to increase electrification of industry. Another important point here is that in this map, we are including the chemical feedstocks. Chemical feedstocks are fossil fuels used as raw materials. So they are not combusted to supply it, but they are used as raw materials. So they cannot really be substituted with electricity, and they represent, as you can see from the plot, a huge chunk of the energy consumption in industry. So then from this, we try to explain what could be the entry points for electrification in the European industry. So we selected processes that are common to all industry sectors. So like, for example, production of steam, drying, and all processes that are operated at low or medium temperature. Then we selected technologies that are already mature, well established. So for example, electric boilers or heat pumps and others. We also selected these technologies based on the fact that they can be implemented in hybrid systems, because we think that an important component in an entry phase of electrification would be to give flexibility to the producers and to adapt to the new system. So to move from a fully combustion system to an hybrid, and then eventually to a fully electric system. So the blue shaded area of this plot shows what could be electrified in this first stage, and it represents 42% of the useful energy demand on industry. And if we remove the feedstocks, then it would be 66% of the thermal energy demand from industry. And this is important because basically we are saying that with existing technologies, we can electrify this share of energy in industry today. Then we move to the second stage. This is not necessarily a subsequent stage that needs to be a follow-up to stage 1, but it's simply different from stage 1 due to the fact that we think it will be more technologically advanced, and it will be more complex to electrify these processes. Like in stage 1, we consider technologies that are already mature and with which industry is already familiar. But these technologies are very specific to either selected sectors, subsectors of industry, or sometimes even differentiate across, so depending on the product. So very, very specific technologies. And that's why we think this will be more technologically challenging. And we see here that in the plot, we see that the purple shaded area represents exactly what could be electrified in stage 2. And these amount to around 50% of the useful energy demand in industry. And if we could exclude the feedstocks, this increases to nearly 80% of the useful energy demand. And again, this is an important result because what we are saying is that with technologies that we already know that are already there and could be readily implemented, we can electrify this much of the energy consumed in industry. Then we move to the first stage, and this would be the stage where we fully electrify industry. Now, obviously, this comes with the high technological uncertainty. And as you can see from the plot, the red shaded area corresponds to what could be electrified in this stage and involves the three critical industry subsectors, chemical, cement, and steel, because they are the most energy and CO2 intensive sectors. And what we have in the case of, what happens in the case of chemicals and cement is that we consider technologies that are not fully developed. So they are being developed, but they are not there yet. And in the case of steel, we make the assumptions that primary steel production is completely offset by secondary steel production. Because in this study, we didn't consider indirect electrification. So we can't consider hydrogen, for example, production of steel with hydrogen. And obviously the most advanced technology to directly electrify steel are electric arc furnaces. But this implies a much more developed circularity of the steel management, and obviously also increasing the scrap availability. So there are certainly technology uncertainties also in this stage. But in the end, with this stage would be implemented, we would have 60% of the useful energy demand in industry electrified. And if we exclude the feedstocks, nearly 99% of the thermal energy demand from industry would be electrified. Then from this analysis, we move to trying to estimate what is the CO2 reduction potential via industry electrification. And in this plot, we see the emissions from industry in 2015 divided into indirect, direct, and process emissions. And then across the three stages, we estimated the emissions, the industrial emissions. We did this for 3 different carbon footprint of electricity. So we used the 300 grams of CO2 per kilowatt hour. There was the average carbon footprint of electricity in Europe in 2015. And what we see is that we have in stage 1 and stage 2 an increase of emissions, obviously. And then in stage 3, suddenly these emissions drop and actually go below the level of industrial emissions in 2015. And this is due to the fact that in stage 3, we have a considerable reduction of final energy consumption, which leads to the decrease in emissions. Then we consider carbon footprint of electricity much lower. So we imply that there is a decarbonization of the power sector. I know, Nico, I probably need to be too close to the presentation. Okay, so we consider these 2 carbon footprints of electricity that are taken from the projections from the IEA ETP from 2017 in Europe, and they correspond to 108 and 12 grams of CO2 per kilowatt hours. And we see that we have already immediately in stage 1 a drop in emissions, and this can reach up to 80% of reduction in emissions compared to the current level. So it's a significant reduction of industrial emissions that can be achieved when industry electrification is supported by a decarbonization of the power sector. And obviously, it would reduce the bottleneck of industrial emissions to process emissions. So in conclusions, from this study, we were able to identify barriers and enablers for the industry electrification. So it's clear that decarbonization and expansion of the power supply are prerequisites for reducing emissions in industry when industry is electrified. So we need to decarbonize and expand the clean power supply to industry. It is important that industry will maximize its demand flexibility and develop new smart approaches to obviously benefit from electrification. So higher flexibility is needed. And then in the case of, in most European countries, powering industrial systems with electricity would lead to an increase of production costs. So it is important that we have policies that support industry in this, if we want to see industry electrified. And this means to reduce the taxation that currently obviously affects the cost of electricity, and also give a clear sign with implementing a carbon price that can obviously sustain a more competitive cost of electricity in the energy market. And that's it. Thank you for the attention. The study you can find here, this address. Thank you for joining and for listening to this presentation.
Yeah, thank you very much. We have one question by Piero, or two questions better, that are on the edge of being more for the general discussion. So could you say shortly something on how to match timescales of diffusion and deployment of these technologies with the different levels of technologies?
So
yeah.
There are here two components. One is the cost. So obviously, the moment industry is not going to move to electrification because the cost of electricity is simply not convenient. If we talk about technology, so the technological development, I think that scaling up is something that requires optimization, implementation, so requires practical applications. And it's not necessarily an engineering problem, but if there is no interest in scaling up, then industry will not make an effort to scale up. And so it's a bit, the more you do, the more you learn, and the more you optimize the process and you make it possible. So when I spoke with producers of technologies like electric furnaces and so on, they didn't seem to see a problem in scaling up these technologies, but they simply don't have an interest in doing so because there is no request, there is no, so we actually don't know how scaling up these technologies, how difficult it would be, but it seems to be more a problem of cost rather than really technical issues, let's say.
Okay, I think we will come back to this question again. So now we have our final presentation by Panagiotis. I think many of you know him. So he has a PhD from the University of Athens. He is a senior researcher and project manager at E3 Modeling since 11 years. So he comes more from an economic background, and he has experience with developing and operating large-scale models, quite a lot, and also a lot of insights and experience in the policy area and the connection between science and policy. So Panagiotis, please share your presentation and good luck.
Thank you very much, Nico, also for the kind words. So I hope that now everybody can see the presentation. So is exactly as Nico very correctly said, the presentation has a more, let's say, economic focus relative to the others. But again, starting from where Silvia left the conversation on what is economic for industries to do and what policy measures can be used to support, especially European industries in their transformation. So industries have begun, let's say, a steady decarbonization progress already from the 90s, at least in the EU. And this is a result of several reasons, like their ETS pricing, energy efficiency, and structural changes, especially with declines in energy-intensive sectors. And there is already some progress in that, but current efforts have to be accelerated in order to bring industries as close as possible to the carbon neutrality goal by 2050. And of course, this has some large technological challenges and most importantly, competitiveness issues which are raised. And I'm gonna present about it. First, on the technology side, we know that a lot of low carbon technologies should be developed and effectively diffused in order to ensure decarbonization of these industries. And the two prominent options, especially in the EU, are the deep electrification, as already presented by Silvia, but also hydrogen applications in industries. So, and what we want to stress here is that ambitious policies in this decade are required because actually the market uptake and diffusion of these options may take a while because all these infrastructure and technologies have long lead time. So this decade, the decade from 2020 to 2030, is absolutely crucial in order to pave the way for these technologies. And previous analysis, for instance, in the Clean Planet for All strategy has shown that this gap to neutrality can close by a combination of several options, ranging from current options like efficiency and electrification, but also some novel carbon neutral technologies like hydrogen, clean gas, and CCUS are absolutely necessary in order to bring European industrial emissions as close as possible to the net zero goal. But the focus now is to assess what this means for the competitiveness of the European industries. So this basically starts from the fact that in the EU now we have very strong policies already in place, both for 2030 and 2050, essentially as part of the European climate law. On the other hand, globally, and especially in other major economies, these policies are not so ambitious, and of course, and this means that there is some continued asymmetry of climate efforts worldwide. So in this context, there are some competitiveness issues raised, especially for the industries that are energy intensive and trade exposed in the EU. Because these industries, of course, if the production costs increase in the EU, they can relocate relatively easily if they are trade exposed, and they can relocate to other non-EU member states, non-EU countries, creating, of course, issues like destruction of jobs and loss of income, etc. And of course, this is something prominent now in the policy debate. And the European Green Deal, and also later the Fit for 55 package, suggested that the carbon border adjustment mechanism can play a role in order to reduce leakage as much as possible, but also help creating a European market for low carbon products, which is critical in order to upscale the low carbon value chains, but also as a pressure mechanism in non-European industries in order to increasingly adopt low carbon technologies, because otherwise they have to pay a carbon taxation in the European borders. So, of course, this CBA is mostly discussed to be implemented in the most vulnerable European industries, which is the vulnerability, at least in the European policy document, is a result of, is a function of trade openness and GHG intensity of production. And you can see here a classification of the most important industrial sectors in the EU, with the usual suspects like basic metals, iron and steel, for instance, non-metallic minerals like cement and chemicals, and paper and pulp also facing the highest leakage exposure. So these are the industries that should be targeted the most by potential measures to protect them. So the discussion about the CBA is a discussion that has been, let's say, going on for a while, and because it can actually, the design of the system actually can take various forms. For instance, a carbon tax can be applied on imports at the European border, or even the imports can be used to extend the European ETS. On the other hand, there are other propositions, like a carbon tax, for instance, to be applied at a consumption level, for instance, as an additional VAT or excise tax. So all these options are now in the policy debate, but most prominently now the discussions about the tax applied on imports at the European border. So this is where we focus this study. But essentially, as this CBA involves changing actually the trade relations between European and non-European countries, it has a lot of challenges going on. For instance, starting from the simplest one, because we have the EU has to ensure compliance with the World Trade Organization rules. Otherwise, these rules cannot be adopted. But also other issues like international revenue transfers, which commonly face political obstacles, or the potential for retaliation measures by non-EU competitors. And several other issues like what rate flows are covered, what emissions are covered, if this includes direct or also embedded emissions, and all that. So there's a lot of challenges that should be, let's say, tackled before this option can actually be used in practical terms from 2025 or 2026 onwards. So in this study, we designed several scenarios in order to assess the macroeconomic impacts of ambitious climate policies in the EU in the context of an EU goes alone type of scenarios, but also the analysis includes the carbon border adjustment mechanism. So in this study, we assume that the CBA is aligned with the EU ETS pricing and applies to products of energy-intensive industries, and it applies to all imported goods, the energy-intensive goods, which are imported from non-EU countries, according to their carbon content. And as I said before, because the issue of export rebates and retaliation measures are something that have a lot of uncertainty, we have decided not to assess them here. And for the analysis, we have used the GEMI3 fit model, which probably most of you have known, which is a multi-regional, multi-sectoral CG model, and Suri market equilibrium. And we use that because it has a very good representation of multiple industrial sectors and endogenous bilateral trade flows. So some very brief results of the analysis, which is already published. First of all, we assessed what is the magnitude of carbon leakage. And we found that when the EU acts alone on climate, I mean, it tries to implement the Fit for 55 package and then the neutrality target, while others only follow the NDC assumptions, which we found that there's significant leakage, around 25% cumulatively by 2050. And this is specifically focused on the energy-intensive and trade-exposed industries. This has very negative impacts both on GDP and employment, which in the EU tend to decline as a result of competitiveness losses in international markets, while we see that major trade partners and countries that are close to the EU tend to benefit from this, because, for instance, Russia or Turkey, which are very close to the European borders, can easily, let's say, the European industry can easily relocate there in order to avoid paying increasing ETS prices. And of course, there's also the environmental negative, because we also see emission increases in non-EU countries as a result of the leakage, especially when the energy-intensive manufacturing is reallocated to countries that have higher carbon intensity than the EU. So all these are problems which should be, let's say, tackled. And here is a figure showing actually the very large impacts on the EU from this scenario, actually with fossil fuel industries, but also the energy-intensive manufacturing industries suffering a lot of losses as a result of ambitious climate policies. While on the other hand, non-EU regions actually face some benefits in terms of improved competitiveness. So now we're coming to assessing what is the role of a CBA mechanism in all that. So we've done a scenario where CBA is actually imposed on on imports from non-EU regions. And the first thing that we found is that CBA can actually be very effective in reducing to zero the relocation and leakage created by asymmetric climate policies. This is very important. I mean, you can show that the effectiveness of this measure can be very, very large, even if this is implemented only in European imports and not exports. The figure here shows that the European shares in energy-intensive productions, they decrease slowly when the EU goes alone for climate, but they increase back again to the reference levels when when CBA is imposed. What is important, of course, to mention here is that implementation challenges remain, right? And we should not forget that this study is a model-based study, so we do not assess any administrative or legal feasibility of the different policy options, because these issues are quite important when you implement these new measures. With regard to the macroeconomic impacts of this, we find that when you impose a CBA, actually the overall, the aggregate impacts on the economy are quite small. But what is actually interesting is that a lot of them, of the impacts, depend on how the carbon revenues are recycled. Because if we use this ETS and carbon and CBA revenues to reduce the labor costs, to reduce, for instance, the social security contributions, which is the option that we have in GEM 3, can actually create a lot of new jobs in the EU and lead to even higher employment outcomes, even than the reference. So this is very, very important options, because actually both ETS and CBA can create some revenues, which if used effectively, can, let's say, lead to double dividends. And on the other hand, we also have high climate benefits in terms of emission reductions, both in the EU, but also in non-EU countries, because non-EU industries, let's say, are pressured in order to adopt less carbon intensive practices.
Can you come to an end?
Yes,
final
remarks. This is the final slide. Thanks, Nico. So some final remarks from the study. The industrial competitiveness of the trade exposed industries will be impacted as a result, especially if the EU acts alone on climate, while others do basically not very much. So this implies some clear risks of industrial relocation. And we found that the carbon border adjustment can be a very good mechanism to protect the domestic manufacturing activity, and especially if we use these revenues in a clever way, let's say, we can ensure double dividends in terms of both socioeconomic and environmental benefits, which is something very, very important. And the last point I want to raise is that in addition to challenges, because we talked a lot about challenges in this webinar, there are also opportunities for European industries, especially if we have these anti-leakage measures, because, for instance, industrial products are indispensable for low carbon solutions, so for renewables, for EVs, etc. So if the EU can, let's say, enhance its low carbon innovation and be, let's say, a first mover in all these new products, then it can create new markets and new export potential growth. So this also activity should be, let's say, should be considered when we analyze the industrial impacts. Yeah, that's it for me. Sorry, one last slide. Yeah, and the article, the published article, can be found here. Thanks a lot.
Thank you very much, Panagiotis. If you send me the, or you can share the link also via the Q&A and chat. Okay.
I will.
So now we have left 20 minutes for discussion. I invite everybody to post into the Q&A, but maybe we have also questions among the panelists or remarks. Otherwise, I have to read what's coming in from the audience.
I have a question for Alex on the presentation on the biofuels. So I would be interested to hear his opinion on, so my understanding is that for the chemical industry and the synthetic fuels that might substitute chemical feedstocks, there would be, or there is an open competition, or if we want to call it competition, I don't know, I'm interested in hearing his opinion, between basically biofuels and fuels that are instead synthesized by using green hydrogen and, for example, carbon capture. So how does he see these two sort of competing or complementary technologies for the chemical feedstocks? So what is his opinion?
Thanks, Silvia. I don't think there is actually there is a regional competition, but globally there are different advantages between countries and regions for these two options that came from BACs, from direct air capture, which is these options are more expensive, are more difficult to be implemented. They have more energy penalties. It's not so easy to have CO2 from direct air capture, but also we can think about also having, for example, CO2 from BACs. So having CO2 from biomass and having hydrogen from electrolysis, and then combining both to have materials. My point here is we need everything. Petroleum is so nice as a feedstock and as a fuel. I know that we want to replace petroleum because of climate change and geopolitics, but actually it's so easy to have organic chemistry from petroleum, from methane, from natural gas, that we need to have different options. And I think we're going to see some competitions in regions, but most of globally, we need to have electric fuels, and these electric fuels will co-produce naphtha. It's impossible to use the Fischer-Tropsch synthesis to produce, for example, diesel or bunker fuels or jet fuels without producing a little bit naphtha. And this naphtha will go to petrochemicals or will go to the gasoline pool. The same is valid for most of the rules related to biomass, to biofuels. Actually, running our model, we firstly expected that the biomaterials will drive the demand for biomass and then will co-produce fuels. But the opposite happens. We have biofuels with CCS, so BACs, and by producing these biofuels for the hard-to-abate sectors, aviation, shipping, and trucks, we produce naphtha. And this naphtha should go to a place, or gasoline or petrochemical. So this is my point. But I think, for example, in Europe, I think the hydrogen pathways will be more competitive than in Brazil. But even in Brazil, we can have some plants with the hydrogen pathways too, but perhaps with CO2 from ethanol. We are thinking about that now in Brazil, to have CO2 from ethanol. It's easy to capture the CO2 from ethanol and to have the hydrogen from electrolysis and then to combine them with the Fischer-Tropsch, with the reverse shift and then the Fischer-Tropsch synthesis. But we need everything. It's not easy to replace petroleum.
Thank you very much. So we have one question. We have one question by Chris Gong, and she asks Panagiotis about the revenue recycling from the COPPE tax adjustment, border tax adjustment, and whether these funds that are recycled to the companies are actually also used to improve the competitiveness and have this positive employment effect that Panagiotis was showing us. So this is more the behavior of the investors in the industrial sector, whether they kind of do what we would hope them to do. Thank
you very much, Nico, and also thank you very much for the question. I mean, indeed, I mean, actually the analysis takes, let's say, how to say, an idealistic perspective, assuming that the government can find effective ways to monitor this process. But yeah, what I want to say is actually that the reduced social security contributions can create some incentives from the firms. I mean, in the EU, there are countries, probably like Germany, I do not know, or others that have very high, a very high share of the labor costs are not actually transferred to the employee. So this is, let's say, this can be a way where you use some additional ETS or CBA revenues to remove this distortion from the economy, because this is, let's say, a very high distortion to the economy. And if you remove some part of it, then it's clear that there are some benefits for the employment. How large? Okay, it is unclear, and of course nobody knows exactly how the companies will behave. This is very, very hard to judge. Yeah, you can only make some assumptions.
There might be also a question on how to design the rebatement and these payments, whether there is some option to earmark these recycled money. Okay, there is another question, and this is about the link between the growth or degrowth scenario that is assumed as the major driver of the materials demand, and how this confronts with the supposedly limited availability of materials, raw materials from the earth, and also energy. So would be good to have some more insights here. And yeah, who would like to take on this question? Alexandre?
I think just, yeah, this is our major target, to model materials as a bottom-up analysis and to understand the material service. I think Roberto had some conversation, some chat with Mariësse, and I think this is the major issue for each team that starts to model industry and materials and global trade and so on, because as of today in our group we are using macroeconometric models and approaches, but we know that these are very fragile, so we need to better represent the materials demand and the linkage between materials and the energy transition, because the energy transition will change the way materials are demanded and the global trade related to materials. So this is, I think, is the major target for us.
Yeah, and from my side, with the image model, I can say that in terms of material demand, it's mostly a growth scenario standard in the model. But as images and the energy model, image is more like an energy model, so it's not inherently intrinsically including materials, and we only have like very simplistic representations of material demand in a model using historical data and just jamming on a statistical model with an S-curve shape in various forms to sort of describe the pattern that we have noticed in history right now, and just extrapolate it into the future with a certain saturation point. That's true. So at some point, I guess demand is met. There's not more demand for per capita than formulated by the statistical model. But that's more or less it. And we do realize that's a limitation. It really limits the decarbonization potential that we have in the model. But there are some experiments going on in redoing that kind of modeling formulation within the image model, coupling demand to the services that the other energy demand models provide. So coupling material demand to, for example, the built environment and the types of housing that is needed. And there is a new project coming up where we are more focusing on other types of material representations like that, more really like describing, I would say, the products that people need in the end, and then relating it back to the material demand. So there's a lot of thoughts about improving that material system that we need to really represent decarbonizations or degrowth or other types of decarbonization strategy perspectives. So yeah, still a lot of work ongoing. And that's it, yeah.
Thank you, Mariësse, and also thank you, Alexandre. Silvia and Panagiotis, do you have something to say? Otherwise, I would continue in the list.
I would just say I would second what Mariësse and Alexandre have said. It's our challenge to improve material representation in IMs.
Yeah, I mean, definitely true. So, Panagiotis, you have been silent on this, but now come again.
Yeah, the same
questions.
is also the same is also for us, right? I mean, it's one of the things to improve, and also consider this degrowth scenario, which seems to be one of the new directions we should take in research. Yeah.
Yes, I'm pretty skeptical about the degrowth scenarios, to be honest, but this is another discussion. Anyways, so we have now to question again to the border tax adjustment mechanisms and the effect on the per capita emissions. So is this really helping? Is this only a kind of a defensive thing, or is there really a overall effect on emissions? And then the dependency, the conditionality of the mechanism to the oil price, and whether you did some sensitivity analysis, so high oil price, low oil price, how does that all change? Yeah, thanks.
Thanks a lot, Nico. Unfortunately, no, have not done such an analysis. It's now we're designing some new scenarios, of course, taking into account the current situation of high import prices in the EU. So probably, yeah, we can rethink of that type of scenario, but unfortunately, we have not done. What I can say is that, yeah, especially the mechanism can be, yeah, quite effective, especially if the production costs are high. So when oil prices are high, because oil and gas prices are high, I am only suspecting that, but probably, yeah, indeed, it's a good question on how sensitive the mechanism is to price sensitivity. Thanks a lot for this. I mean, we take this for future research. And with regard to the first one, indeed, I have mentioned it that in the presentation there are environmental benefits. So emissions decline both in the EU and non-EU, because non-EU industries start using more low carbon equipment in order to produce the same industrial products, right? Because for them it's like paying an ETS price or an ETS CO2 price for their exports to the EU. But the effect is not that large, I have to admit. I mean, it's not. So basically, yeah, I see CBAM more like a protection mechanism for European industries rather than an instrument that can drive very deep decarbonization. It has some effects, but not very high, at least in our simulations.
So thank you very much. I'm running out of questions from the audience, and we have 5 minutes left. I mean, we have had another question earlier also on the price level of the renewables. This was, I guess, directed to Silvia, and whether we can expect really that the price of electricity remains low when we have the climate policy, which is, so to say, kind of a prerequisite for the electrification also. Maybe you want to say something on that?
Yes, well, definitely we need the right policy environment to support this shift in the price of electricity versus fossil fuels. And this year we published, I think, an interesting paper on this question that might provide an answer to this question. We published this paper, which is the results of a modeling exercise with the Remind model developed here at PIC. And you can see that based on a certain policy environment, so certain carbon pricing, but also an assumption of technological development in renewable, continuous technological development in renewables, you have by 2040 electricity becoming the cheapest energy carrier in a 1.5 degree scenario. So basically this is possible if there is a certain carbon pricing and policy support. But yeah, this will depend also, for example, the taxation of electricity. Today we know that affects a lot. So actually half of the price of the cost of electricity is taxes. So then yeah. And maybe I will post a link to this paper in the chat.
Okay, then there was another more methodological question to Alex, because you have such an elaborate model for the materials and the refineries. So you cover a whole range of the heterogeneity of the products and processes. How do you model the demands for this? What is your approach here?
Yeah, and in terms of petrochemicals, not fuel, we stopped in the integrated assessment model in the supply of the first generation petrochemicals. So the second generation, I mean, we stopped the supply in ethylene, propylene, and BTX and butadiene and so on. But we know that this supply is driven by the demand for the second generation petrochemicals and plastics. So we have another model that provides this demand and translate it in the basic petrochemicals. My point before is that this other model is pretty much based on econometric approaches. So we don't have in this, as of today, in this model to the demand of representing the demand for petrochemicals, a very nice approach that gives us, for example, the possibility to forecast some drastic changes and replacements and so on. So as of today, we have a very fragile or conservative demand projections of petrochemicals. In terms of fuels, our model is very detailed in terms of liquid fuels. We have two types of diesel, jet fuels, gasolines, and we compose these fuels inside the Brazilian integrated assessment model. So that's why we can see the intermediary products. So we produce naphtha, and naphtha can compose the pool of gasoline and can compose the pool of petrochemicals. We produce distillates. The distillates can compose the pool of diesel or compose the pool of jet fuel. So depending on the demand, the model choose. And the same for the hydrogen. We have the hydrogen as an energy carrier, but also as a feedstock for refineries or biofuel plants and so on. So we have this type of representation, mostly in our BLUES model.
Okay, thank you very much. So we are in the final minute of this seminar now. There was also a question by Elena on whether the currently high gas price, probably not only the high gas price, but also the political developments that led into this and currently are going on, is a wake-up call for electrification also in the industry sector to improve the energy independence. And yeah, I think this is a very good question, but we ran out of time. It's probably not only a matter of prices, I would say, because also the electricity price in some countries is driven by the gas price. Yeah, don't forget that. Here in Europe, I don't know how it's in Brazil, but here in Europe it is. So the gas price effect would not automatically lead probably to a electrification of the industry sector. Okay, I leave it with this. I thank our panelists, big hand from my side, and also the great questions that we have had during the seminar. Thank you very much and have a nice day, everybody.